All right, so today I'm going to be talking about a new Python visualization library that we just put out like a week ago. And I'll also be giving a quick demo, so I hope that my demo goes even remotely as well as the last one. So the visualization library that we just put out is called Setmlvis, and it's used to compare different object detection models using set visualizations. And set visualizations may not make sense yet, but hopefully at the end of this presentation, you can get a better sense of what that is and how we're using them. So a little bit about me. I'm a fourth year PhD student at Northeastern University, and I'm a member of the Data Visualization Lab. So a lot of my work isn't as technical, and we're kind of partnered with people who do object detection to help give them visual solutions rather than improving or making algorithmic improvements to object detection models. If you're interested in connecting with me, any of those socials will work well. All right, so what is Setmlvis? So it's a visual analysis tool used in Jupyter notebooks to compare object detection models. And this is pretty similar to maybe Voxel, but we try to hit a specific niche as opposed to many, many things that Voxel can do. And what we're looking for is can we find similarities and differences between model predictions? Now, what do I mean by that? So if we're looking at an image such as this, and we have two cars, we have model green makes a prediction on this car, the light car, and model red makes a prediction on the SUV, you find that they have pretty similar aggregate metrics. But looking at the data and seeing where these models make their specific detections, you can see that model green might be better at doing sedan and light colored cars, or model red could be better at SUVs or dark colored cars. Knowing that, we're interested to see, do different models make the same or different detections? And can we scale this kind of questioning up to a larger system or visual system? Now, we didn't come up with this problem. We had object detection researchers that work in an Army lab come to us, and they had a problem where they had many different object detection models, and they wanted to compare them all and kind of get, especially visually, and see how were they the same or how were they different. And when they were doing the aggregate metrics and making like precision recall curves, it's pretty similar performance amongst all the models. And this is the kind of data they were working with. It was satellite imagery, and they were looking for cars. And I know this looks like CIS blurry image, but trust me, there's many cars in each of these satellite images. And when they were evaluating it, looking into it, they were just plotting it in matplotlib and plotting the bounding boxes over top. So what we did first is, they wanted to see how, they asked us, can you explain how these models are different? They wanted us to look at the images and create some kind of way to, so that they can demonstrate to other people how their models are different. And they wanted to see what kind of objects does one model detect and the other doesn't. So when we looked at them, we first imported them into Voxel. And if we're just looking at one image and all the cars in the image, it can be pretty hard to tell where, for instance, model yellow is different than model green or model red is different than model brown. Just looking like this. Obviously, we can layer them, click different filters, apply things on and off. But again, even in one image, this takes a lot to find those small, subtle differences. And this is compounded when we have hundreds of images and we have dozens of detections per image. So when we were looking through, we might find something that was interesting, and then we had to keep that mentally in our heads as we went through other images and write it all down. We were trying to see like which detections did the different models actually agree on. So when they asked us, how are these models different? We needed to find where the models make similar or different detections. And how we do this is by matching detections. When we look at our original thing, we see, does model green make the same predictions as model red? So obviously here, these two models do not match on this detection or the object. They detect two different objects. And this kind of Venn diagram thing will help us understand the set visualization point later. So what our system does is it matches all the detections between all the different models, and then we're going to use an interactive visual system to actually explore that data. So our research questions were, we wanted to first see what kind of objects or detections do all models agree on. Of all those models, what kind of objects were simplest to detect, maybe what they needed more training data of, where all the models did poorly on. Then more importantly, we also wanted to see where does one model make a detection that no other model does. So if we have 4 or 5 models, where does one model make a detection? And this kind of highlights its maybe unique strengths or its unique weaknesses. And then also which models are similar or are they different? So if we have different architectures, different training styles, are they making the same kind of detections? So what kind of objects detections do all models agree on? Our first research question. And I'll take you through another simple example before we jump into the demo. So here we have a few cars in a suburban neighborhood. We have 3 models, a red, blue, green model, and they all clearly detect these 2 different cars. So if we're looking at a Venn diagram, these 2 objects are detected by all 3 models. In our visualization system, that looks like this. If the model makes a detection or is in a set, it has a black circle and it's filled in. And then we add those detections to the top to kind of keep track of those detections. And this will be later how we use those bars to actually dive into the data and explore it. Now, where does one model make a detection that no other model does? Let's say the red model detects this car behind a tree. So the red model is actually better at occluded objects. We see that it's a unique detection. No other model here is making that detection. And in our visualization system, we have a filled in black circle for red, which means it is the one making a detection on that object, and the green and blue are not making a detection on that object. And there, another blue stacked chart. And then finally, which models are most similar and different? So looking again here, we can see that the red model finds another occluded car, while the green and blue both detect in another SUV. So here, the Venn diagram, we have 2 unique detections by red, 2 that they all detect, and 1 that green and blue detect. And going back to our visual, we have green and blue filled in, and we have the detection added. And then we have another detection added for the red. We can see that, for instance, green and blue are really similar as they make all the same detections, while model red has different detections. It does much better, for instance, on occluded vehicles. Now we take this general concept, really simple visual, and we make it larger. This is what the visualization system is going to look like in our actual, in the Jupyter widget that we have. And this allows us to add more models and have hundreds of detections to be able to explore. So now I can show it in action. Let's go through our 3 research questions again. First is, what kind of objects do all models agree on? Where does one model make a detection that no other model does? And which models are similar and different? All right, so first, what kind of objects do all models agree on? So I hope people can see this. Yeah, this is my first open source library, so I'm learning how to create documentation and seeing that it doesn't always work, so hopefully it does this time around. We have a really simple install where it's just pip install setmlvis. This is what the data set looks like, and in the getting started notebook that will be linked, we have some sample data to work with. And then for the actual running of this visualization system, all you need to do is import 2 different functions. The first function here simply takes all the different models and their predictions and does that matching that we were talking about and I was showing earlier. And then we can launch the visualization widget, which shows us the set visualization, allows us to explore the data. So one thing that we can start off with is by lowering the IOU. And to be clear, the blue here is true positive detections and the red is false positives. And we can bump up the confidence to help increase some of those incorrect detections. And when we click here, we see all the different detections and the different images. So as I said earlier, we were looking at where do all the different models agree? What kind of images do all the different models work well on? So here we have model 1, 2, 3, and 4, and they're all filled in. So this is where all the models agree on a certain detection. So looking at any of these here, you have to trust me because it's pretty small, but there's a car. So all the models agree, and they generally do pretty well in suburban images. We see a lot of true positives in these suburban landscapes. Then if we look at where do all the models agree, but they make an incorrect detection, we're seeing a lot of arid landscapes. And as you'll see here, we can click on this landscape, highlight the different model predictions, and we see that all 4 of the models generally think that bushes are cars, which might be a good indicator that we need more training data from arid landscapes as opposed to suburban landscapes. So when we looked at what kind of objects do all models agree on, we have this where all 4 models agree. We have the blue being the true positives, and we see that in general, the models do well when it's in suburban landscapes, and they do poorly in these kind of arid landscapes where they think that bushes are cars. Now let's answer the next question. Where does one model make a detection that no other model does? So this helps us highlight the unique strengths or differences of the 4 models. So looking back at our visualization here, we select where model 2 makes predictions and none of the other models do. So this is where it kind of goes off by itself and makes its own predictions and the other models don't agree. And if we look at these images, we see generally that model 2 is making predictions on airplanes, thinking that they are cars. Let's see more of that. So where does one model make a detection that no other model does? So we look where there is a single black circle, meaning only one model is making a detection. The other models do not agree that there is an object where that model is making a detection. And we find that model 2 it easily and quickly isolates all those detections that model 2 is singularly making. And we find that model 2 is regularly making predictions that planes are cars. So something in the training or the hyperparameters is causing that. So you have model 2 detects planes as cars. And then finally, which models are most similar or different? Now we've created kind of a query system, which allows us to isolate, make selections of the data. So for instance, if we wanted to look at detections that model 3 makes, but model 4 does not, we click the black circle or model 3 and the white circle for model 4 and confirm. Clicking on the true positives shows us all the places that model 3 makes a detection and model 4 does not. And if we click through, we're able, and again, it's really small, but you'll have to take my word for it. They're all black cars that model 3 is correctly identifying and model 4 is not. And you can imagine that this kind of system could also be used if you have multiple iterations on a model. So if you have version 1, version 2, version 3, and you want to see where is version 3 making predictions that version 2 is not, you could use this kind of querying system. On the other hand, if we look where model 4 makes a prediction and model 3 does not, and we hit confirm, we find the opposite is true, and model 4 is actually very good at predicting white cars while model 3 is not. So now we can go back. We can see which models are most similar, different. So if we click where's model 3 making a prediction while model 4 is not, It's another super grainy image, but it's a black car, and Model 3 detects black cars better than Model 4. On the other hand, if we reverse that query and see where Model 4 is making predictions that Model 3 is not, we have a white car, showing that Model 4 generally detects white cars better than Model 3. So we're learning stuff about each of these models. Okay, I see there's a hand raised, but I'm just gonna wait till the end because I'm close. So just to recap, what we did is we put all these different detections, that this overwhelming visual clutter that can happen, especially in something like satellite imagery, and we parse the data into these usable data slices that we can investigate and go through by clicking, querying, and adjusting the different parameters. So it makes this kind of overwhelming visual scene into more navigable chunks. All right, so recap, what we do is we match different model detections. So whether the models are making the same predictions or they're making different predictions. We put this into subsets of the data, as we showed earlier, which is what we call a set visualization. We input it into our visual interface. So we take this small example and we can scale this to up to like 7 or 8 models and hundreds of detections. And then we allow people to click through and explore and compare the different models. And yeah, so we just released this a week ago and we just got it working in Google Colab yesterday. So please give it a go if you want to try it out on the Getting Started notebook. If you are interested in seeing how it works with your data, we can work with you and you can reach out to me. We can see if we can find any insights, with your real world data. Yeah, and that's all. And I can go through the questions now.
Yeah, we got a ton of them, so there's plenty in the Q&A. So if you did raise your hand, it's going to be faster and better to just ask that question in the Q&A.
Um, all right, so Noriko, for example, if there is a moving car, etc., which may be lost by hiding behind a wall and then appearing. So we are working with still images currently. This sounds more like a video thing. Again, comparing class of those two are the same card. No, yeah, it cannot do that, because yeah, it's just still images. Originally we started working with video, but it was too complicated for our system. Next question is Setml is very impressive. How did you code the stack? So it's a Jupyter widget extension. I did a lot of design. I have another person that works with me, and it's coded in Svelte. And it's basically a web page put into a Jupyter cell block. Then all the data pre-processing is done with Python, and we try to make it in Jupyter notebooks because generally people work in Python and Jupyter notebooks, especially on computer vision. Is there a research paper? Hopefully, in the next 3 or 4 months, there will be. There is currently not. I am writing it. Your example seems like Setmlvis is more good to find the same ships on ocean which have taken an image by satellite or one time frame after the satellite circulated and back to the ship's move. They can. Is this correct? Understand? I don't think it's exactly the correct understanding. It's not to compare moving objects. We have the many models trained on one set of images, and we want to compare the different models on the same set of images, kind of like benchmarking, and that's what it's good for. Um, can all these models be combined for a more perfect prediction and be trained for real landscapes? Well, so one thing we've been thinking as an extension is using SetML to be able to do better ensemble methods. As you could see here, when all the models agree, we generally have much better prediction success. And when they go off on their own, they're making more negative predictions or incorrect predictions. The people that we work with in the Army want us to see like how well this works if there's no ground truth, and like finding a correct ensemble method or subset of models and combining them to have the best possible accuracy. Are they really taking satellites for this, or is this imagery from drones? I do not know. This data set was handed off to us. We didn't do the collection or anything.